Good question. So, in general, from what we have observed in many measurements, in general, there are, at the end, there are 3 channels, but one of these channels is very highly transmissive, and the other ones have transmissions which are very small. If you have transmissions which are very small, the frequency of at phase equal pi, you see at phase equal pi, you get 2 delta square root of 1 minus tau. If the transmission is small, then this frequency is very close to the gap, and then this would never cross the resonator.
So that's just before breaking?
Yes, exactly. This is just, you see, these high transmissions you only obtain when you have, exactly. So at phase equal pi, here what I show is the same as before. This is the IQ plane. So this is I, this is Q, and this is how we can distinguish between the 3 states. So this is in the dispersive case, and here we can see that most of the time, so here we are not exciting, we are just sending measurement of measuring the resonator. So we measure the resonator, we get the point. We measure the resonator, we get the point. We measure the resonator, and we repeat, and we build these histograms. And so we see many times, so here I say, yes, it's 10 to the 4, so 10,000 pulses to measure points here. So most of the time, almost 45% of the time, we are in the ground state. Sometimes we are in the excited state due to thermal excitation, and there are 50% of the time we are in the odd states. And this is because this is a problem for all superconducting devices. There is quasi-particle poisoning. What is poisoning? Is you have some quasi-particles which are close to the superconducting electrodes, and these quasi-particles, they see that there is a weak link with a state which has lower energy, and they go and they live there some time, then they leave. So these things we have 50% of the time, and there is nothing we can do about it.
So
yes?
This is with thermal excitation of those quasi-particles? So
this is, if you know, for superconducting devices, if you calculate which is the density of quasi-particles that you should have out of equilibrium, at equilibrium in the superconducting electrodes at low temperature is negligible. But you have some out of equilibrium quasi-particles which nobody knows the origin, and they can poison. This is a problem for charged devices and for our system also, which is sensitive to the parity. So this is a single shot. What does single shot mean? Is that we need to measure just one point. So we send one time a pulse to measure the resonator, and we know if our point is here or here or here, we know which state we are. For the qubits, for the superconducting qubits, in order to be one shot, they need to put a lot of power, and the problem is that when they start to put a lot of power, then since it is a continuous potential, they start to populate more states in this anharmonic potential. In our case, we can put as many photons as we want, because in principle there are just 2 states. There are not more states. So this is a true 2-level system. So this is a picture of just indicating. So here we have no quasi-particle, just the ground state. The current is flowing in some direction. One quasi-particle, there is no supercurrent. And when we have 2 quasi-particles, the current is flowing in the excited state, is flowing in the other direction in the loop. Okay. Just a cartoon. So now we can play and use these tools that Paul explained of quantum manipulation. And the idea is the following. So let's this is really, it's like the problems I'm sure you solved in quantum mechanics. So you have 2-level system, and you applied a cosinus omega drive, and then you see how the population of your states evolve in time. So the idea is the following. So we have ground state, this is the Bloch sphere. We have ground state pointing, this is like spin pointing up. We have excited state, which is the spin pointing down. And what we are going to do is to apply some field, which is going to do some precession between up and down states. Okay? This is what we do essentially is we send another microwave at just the frequency of the transition, and we measure. So what we do is, it is going to be explained in a second. So what we do is, we apply this tone So we apply this drive during some time, and then we measure. We wait. We apply this drive during some time, and then we measure, and then we repeat. Every time we measure, so the system evolves during this time, then we measure, and when we measure, we have some probability of being in ground state, or in excited state, or in odd state, which is not shown here, because there is no evolution. So with this, doing this many times, we can extract the probability of being in ground and the probability of being in the excited state, and show this as a function of the length of this, for example, as the length of this tone. And what we observe is the following. So this is, finally, I arrived to explain what you were seeing. So you can see how this is the time of the duration of this pulse. And as the time is longer, we observe this transfer of population between the ground and the excited state. You can see here, what I'm showing is just the population. So the renormalized population. So this is the amount of points that there are in each of these clouds. You can see that the odd state is not at all perturbed by what I'm doing. This population is almost 0.5, so 50% of the time I'm in this state, and this is nothing to do. So this is the first observation of the coherent manipulation of Andreev states. And you can see there is some, of course, these Rabi oscillations do not live forever. There is some relaxation. And we can measure, which is, for example, the lifetime of our system. So there is, okay, so this is just a cartoon showing the same thing. In particular, there is this point here where the transfer of population is maximal, okay? So here you start from the ground state, which is almost mostly populated, and then you inverse the population, so you get the ground state is less populated than the excited state. So this is equivalent to say in the Bloch sphere that you find which is the time you need to take this spin pointing up to spin pointing down. This is known as a pi pulse because you make a rotation from your spin to up to down, okay? And with this pi pulse we can prepare our system. So what we do now is the following. So we apply a pi pulse. So we are in the ground state, we put the system in the excited state, and then we wait some time, and then we measure. So this is this delay time. So this is a measurement this is a measurement of the population of each state as a function of this delay time. If I don't wait, if I measure immediately, I find that everything is in the excited state because I just make this and measure. Everything is in the excited state. But as soon as I wait more, I find less and less population in this excited state, and this exponential decrease gives the lifetime of my excited state. It's like saying, I put the system here, but I wait, and then I find that the system is a bit here, a bit here, a bit here. So it's not exactly as in the same place as I left it. So this time is 4 microseconds. You can see this is not very nice qubit, and this is not what we wanted to do, just to show how long this state lives. And we have some other studies of which are the origins of the relaxation. This is very complicated problem. The other thing that you may do is, as Paul explained, is to characterize what is called the coherence. So what happens if I apply a pulse which is pi over 2? If I apply a pulse which is pi over 2, I start with the spin pointing up. I apply this pulse, I arrive to this equator of this sphere, and in the equator of this sphere I'm half ground, half up and half down. So half ground state and half excited state. So this superposition here in the equator of the sphere in general has the problem that if the energy of my two-level system is fluctuating, there is some dephasing in this sphere. Here you can see, but I don't know if you can see, there are some arrows here. So there are probabilities of finding the system in different living at different places in this equator. So the sequence that is normally used is called Ramsey sequence, and the idea is the following. So you apply the pi over 2 pulse. You are here in the equator. You wait some time, which is this free evolution time, and then you apply another pi over 2 pulse. If you don't wait anything, it's like applying a pi pulse, okay? It's just pi pulse. But if you wait some time, there is some relaxation, some decreasing of these oscillations, and there are oscillations because the frequency of this tone is not exactly at the resonant frequency, because it's easier to fit oscillating expression. So essentially we get some coherence time which is 40 nanoseconds, which is very bad. If you want to do a qubit with this, you are dead. So just don't try. What is nice is that you can do echo. So this is an example of echo. The idea is the following. So you apply the pi over 2. You arrive to this equator. You are here in the equator. There is some dephasing, some decoherence. And then what you do is you apply a pi pulse. A pi pulse, what it's going to do is to rotate everything from this point to this point. So all the dephasing that was doing this is like a time reverse. So now you get an echo because there is some refocusing on all these situations in which the state was just giving some decoherence. In this case, you get this time, which is called T2 echo, which is larger, which is 600 nanoseconds, and this would imply that we have a lot of low frequency noise causing decoherence. So, okay, so I think this is one example, and now I'm going to show two different things now. So questions up to here. This is like, I'm going to change slightly, but I'm going to continue with this idea of coupling microwave resonators using c-QED setup with the Andreev system.
How important is the separation between the ground state and the excited state of the Andreev Bound States?
How important is, so you need, so to be well in the dispersive regime, you need to be, so in general, I mean, you need this frequency difference to be much larger than your coupling. This is, I think, the important condition to fit well with these ideas of state readout, to not mess up with your identification of the state. This is okay. So yes.
We're going to speak about red and the blue states, right? So the green one, does it involve in any of these processes? The green state, so the old state, does it involve in T2 or T1 time?
Yeah, that's a very good question. So, in principle, one would like to say that the microwave photons. So how could be implied? So how can this be? So you are sending photons for proving your resonator and also to excite the transitions, okay? But the frequency of these photons are very much smaller compared to delta. So all what has to do with quasi-particle, creating quasi-particle and everything is related with an energy which is delta or 2 delta, depend on the model. And we are considering frequency, so in aluminum, let me say, in aluminum, delta is 45 gigahertz and 2 delta is 90 giga. We are working at 10 at not much photons. So we believe that this, in principle, all which is related to this odd state has to do with other mechanisms, not with the, okay. Because of the energy, essentially. Yes?
So you were presenting the change mechanics and I told you
yes.
the interaction. So isn't there an additional interaction term containing sigma z, so that component?
Yes, this is just renormalizing the frequency, but you can see, I have some slide, but that this is important far away from pi. At pi, there is some cosinus term which is some cosinus delta over 2, some term which is just cancelling. So. But in any case, it would be just a renormalization of frequency, which you would never see because you don't see which is the bare frequency. So I'm going to comment experiments in a different setup, which are indium arsenide nanowires, because this is like very studied in these days, and I think that there are some nice results. So one experiment doing this direct microwave measurement of Andreev Bound state dynamics in semiconducting nanowires. So it's the same, following the same ideas. These experiments were performed by Michel Deboré Heiss in Yale, using samples from Attila Geresdi. I don't know. Yes, here Attila Geresdi from Delft. So this is the setup. If I don't explain, you won't understand. But let me start from the first thing. So this is the nanowire here, and this in light blue is the aluminum. So this is a system which is a junction where you have the nanowire. There is some this is what is called two facets. So they take the nanowire, they deposit aluminum on two facets of this hexagonal nanowire, and this is and in the middle they just etch the aluminum. So you have a junction between superconductor, and in the middle there is a junction. Okay. So here, as I explained, there are Andreev states that form, or that's what they hope to have. Here in magenta, this is a gate. So because the nanowires, you can apply a gate voltage and you can gate your nanowire. So this gate here is just is here. This gate is gate voltage is this line which you don't see but ends like here. Okay, there is a gate. The rest is, so this wire here is embedded in a superconducting loop which is shown here in green. So this in green is also the superconducting loop in order to impose the phase bias. So it's the same idea. So the difference is that with the atomic contacts we can just play with our mechanics setup to control the transmission. Here they can play with the gate to control the number of channels and the transmissions. Okay. So here in yellow there is this microwave resonator, which is a different resonator, which is a slot line. So this is just two electrodes and it's resonating like this. So the excitation here is just it's a special mode. But you can see this is just a microwave resonator. Doesn't matter. And what they do is they measure the resonator and they send photons here in this with this line to excite transitions. The same as I showed. So I summarize the results. So this is the phase of the reflected photons. They also measure in reflection. This is the phase of the frequency, and they measure this as a function of the gate voltage. So this is what they observed. So nothing happens until at some gate voltages the phase starts to do something like this. When they make a zoom here, you'll see that the phase is doing chick tack tack tack. So here there is an anti-crossing. This implies that there is some Andreev state that is crossing this resonator. Okay, they stay at this close to this voltage, and they measure. So what they do is they send photons to excite the transition as a function of the phase difference, the same as I showed before, and they can see this Andreev spectrum, this line, and they can also give a fitting for the transmission. So you can just go to the paper and see the details, but they also see this in the dispersive case. So staying here, they can also see these three clouds where they can find the system either in the ground state, in the excited state, and they also find this odd state. Well, they do all the same coherent manipulation. This is a nice example, and what they are interested in here, one of the main points of the paper is given what is called a parity lifetime. What is a parity lifetime? Is the time the system remains in even parity before a quasi-particle arrives, because this is going to be a relevant parameters for all these Majorana qubit proposals. Okay, they don't want parity switchings. Okay, so this is the experiment, and I will present the experiment that we were doing this very last summer. So we had, instead of using these two facets nanowires, so these nanowires are grown in Copenhagen by Peter Cross Group and Jasper Nygaard. And the idea is, as I explained yesterday, so we have these indium arsenide nanowires, which are semiconductor, and they are full covered by aluminum. Okay, so the proximity effect is very, very good in these wires. So what we do to tailor our weak link, we etch the aluminum in some region, which is, this case is 400 nanometers. So we etch the aluminum here, so we get a junction which is superconductor and indium arsenide, naked indium arsenide. In principle, just a normal wire. This in yellow, this is a metallic electrode. This is a gate that we use to gate the nanowire. Okay, just simply as this. So this nanowire, as before, is placed in a superconducting loop, as before, and this is coupled to the end of a microwave resonator. So this, in a second, is going to be a microwave resonator. So in this case, so the microwave resonator is this meander line. So this is open here you have this electromagnetic wave propagating along this line, and at the end part of this resonator there is a short circuit. So you can imagine the wave is just reflected at this point, and at resonance, as before, you have a maximum of the current. So a maximum of the current here is going to couple with this loop. Okay? Yes. 10 minutes. Yes, I'm finishing in 5 minutes. So what we do is essentially the same, measuring the I and Q signal as before. As we send photons here, so here we send photons at the frequency F1, and we change the phase difference by threading a magnetic flux. Again, so the same experimental idea. So what we observe, so the color here, so this is complicated, so the color here encodes the shift of the resonator. All what we measure is how the resonator is shifting. The axis here is the frequency of the photons we send to excite transitions. And here is the phase difference that we control with the little coil. What we observe here, there are many transitions. There are many, we can observe many transitions, so many Andreev processes, so many excitations can be inside this weak link. From all this complicated spectrum, we highlight two features. So one is this feature, which is very much like here, which is called an even transition. This is the same transition we were observing before, just that before this is phase equal pi, we were very close to this end. Now we are measuring something which is from pi to 0, and this is showing that this is 2 times periodic. The reason, I have not put all the explanation of this, I'm just going to say the reason that we observe this completely spectrum is because the weak link now is long. And since we are in the long limit, you expect that in the long limit you can measure Andreev states up to phase equals 0 and pi, okay? Details I can discuss, no problem. So this is the first observation of the spectrum of Andreev states in the long junction. So
why your Andreev states are not flat if you are in the long junction limit?
They are really flat. If you compare, you will see the fitting, but this is they are quite flat. There are other features, which are these bundles of lines. Okay, these lines here, you can see there are these lines that are closing at phase equal 0 and phase equal pi, and these lines are splitting into 4 and then closing again. And these lines originate from the fact that inside the nanowire there is spin-orbit coupling. So when you have many channels in the wire, in the long limit and with the spin-orbit coupling, you can get these types of solutions, and I will explain in a second a model to which is the spectrum that originate these transitions. These transitions are indicated here as said odd. These are odd transitions because there are transitions that need that there are quasi-particles present in the system, and we can promote these quasi-particles to other excited states. Okay? So let's see, for example, here with the gate voltage, we can just tune the wire and then go to another situation. So this is another example where we can also see these bundles of 4 transition lines. This is also, as I will show, these are a consequence of having inside the system a spectrum of Andreev states which are spin split. And this is also the first observation of 0 field, there is no applied magnetic field, 0 field spin split Andreev states. So, with the colleagues in Madrid, Alfredo Levi-Yeyati, yes?
The whole thing is a magnetic field, right?
Sorry?
Isn't the whole thing a magnetic field? So the flat.
The only, yes, this is micro Tesla. This is completely negligible. So the energy of this field is doing anything. So Alfredo and Sungun Park in Madrid, they developed a theory in which in the long limit, so in a long junction with spin-orbit coupling, you can get Andreev states which look like this. So before we had Andreev state, we were starting in delta, and we were coming just until some minimum. Here I'm just showing between 0 and delta, okay? Not the negative part, because this is excitation spectrum. And so now instead in this long limit we have this state which are now spin split, and the transitions that we observe are either we go from the ground state and we put two quasi-particles here, or we start with one quasi-particle and then we promote this quasi-particle to the other state. This transition gives rise to these lines, which agrees. We have nice agreement with the theory. I'm not explaining it completely, and I'm open to questions if you want. So just to say that this theory accounts very well for some of the features of the spectrum, in particular this bundle of lines, but also it can explain the behavior with magnetic field, because if these states are spin split, one would expect that if I put a magnetic field, like now a real magnetic field, this state would move differently, okay, because of the spin species. So let's see what happens. So here we have two coils. We have now big coils to apply a field which is in the plane of the wire. So this is the plane of the wire, and we can apply a field in an arbitrary direction. In particular here we have, because at the beginning we didn't know which was the angle of the wire with the good precision, then we will find out. So when we have a field which is, for example, with 45 degrees with the wire, you observe that at zero field this is a sum here at phase equal pi, and at phase equals 0. This is these little squares here. So you can see the spectrum is very symmetric, and as we put the field, so this is 2.6 millitesla, this is like very small fields, and 4.4 millitesla, then you see that this spectrum becomes asymmetric. There is one of these lines that goes down and the other line that goes up. And as we increase, this effect continues. So the lines really moves differently. So the problem here, so if we put the theory, so the theory is the green lines, they describe quite well the behavior of this, how these Andreev states move with magnetic field. But the problem here is that we have both components, so perpendicular to the wire and parallel to the wire, mixed at the same time. So what we did is just to start rotating until we could find some, isolate the two behaviors separately. So here I present, so this is at zero field, the spectrum is very symmetric. So here is when the field is perpendicular to the wire, we observe a very asymmetric, one of the line goes up and the other one goes down, like here. So this is for increasing field, 4 millitesla, 8 millitesla. And when the field is completely parallel, the only effect is a partial, so a splitting of the Andreev state here. So splitting of the line, so you see there is a partial splitting of. So this is very recent work, and yeah, this is on the archive after this month. So you can. I thought I had a reference, but this now is gone. So there is no more reference. So with this, I conclude. I finished, and I'm open to questions.